أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. I welcome you all in our today's online session. Hope you all are fine and having good health. We'll start today's session with the verse of Holy Quran. Hopefully my voice is clear at your end and screen share as well at your end. Uh, we'll start today's session. Further going towards the lecture. So last we discussed about the concept of Simpson's 3-8 rule at 8 interval and 9 iterations. So 8 intervals can also be set in 9 subintervals, and we can also call it 8 intervals at 9 iterations. And it's a technique of numerical integration iterative method in which we need to calculate the numerical integration. So Simpson's 8 rule also provide the value of area under the curve. That integration from the starting or ending value from the lower and upper limit 0 to 9 having the function x square d of x. Using composite Simpson's 3-8 rule, we have 8 intervals towards the 9 iterations. First, we need to calculate the value of h. And for h, we have the formula b minus a over n equal to 9 minus 0 divided by n number of iterations equal to 1. So this is the way that how we can find the value of h. And putting the value of each and every individual from 0 to 9, because we have the starting value 0 starting from the lower interval and h the iterative difference having value 1. From the lower interval value, lower limit, add each of one iteration 0 plus 1, 1 plus 1, and 2 plus 1. We have increased the iteration from 0 at the interval with the interval 1, and a series of values 0 to 9 would be formed in this way. Each and every value of 0, 1, etc. place in the function f of x, that is x square, and we got the value over here. Same the pattern we follow in class, that we find the value by placing x. We form a table of column f of x equal to x square. Over here, you can see these two columns of x and f of x we form. We need this formation of table for Simpson's 3-8 rule formula. In class yesterday, I already write down. Hopefully, you are aware of this. The Simpson's 3-8 rule formula for numerical integration area under the curve. That iterative value of area under the curve we need to find by the formula 3 divided by 8. That is the 3-8 rule. Multiply by h. That is the iterative interval. Multiplied by all the values that is starting from, we can set it's from f0 to f8 and f1 to f9. So this is the way that we can place over here. So the generalized formula, in if it is written in f0, we can also write f1 instead of f0. So that the concept already discussed in last class. And further, f0 plus fn. F0 is the starting value and fn is the last value. All the summation value, that is multiple of 3 summation of f of I, iterative values, plus 2 summation of f of j. All the value of multiple of 3 and all the value of multiple of 2 uh, instead of f naught and fn from the starting and ending value, we got these two aspects. So four aspects we got in bracket, that is f naught, fn, that is the starting and last value, and three summation of fi plus two summation of fg. Over this concept, we further coming towards the third step that applied that formula. So we add all the values from f1 to f8 over here instead of 3, f3 and f6. So f3 and f6, that is multiple of 3 and multiple of 2. So all the summation value from this way and in between these things. So 3 multiplied by h divided by 8. This is the generalized form of the formula. 0 is the starting value and 81 is the last value. 159 multiple of 3 and 45 multiplied by 2. So this is the way that we can written in this form. So 159 is the multiple of 3 and 45 is the multiple of 2. We follow the concept of the last pattern of the Simpson 3-8 rule, that formula of the format is f1 and f9 starting ending value plus 332 332. This is the concept that we follow. So 332 and 332 we follow over here. So add all the value after multiplication. 3 multiplied by 1 divided by 8 would be generalized way in this form. And after that, all the value after the addition, we got 360, 348. Multiply by 3 divided by 8. So we got the last value, iterative, numerical iterative 3-8 rule, 243. Further, the exact integration that we found by the iterative, instead of iteration, we conventional method follow the integration, that the lower and upper limit 0 to 9 x square d of x. So we integrate the value. The internal function is x cube over 3. And by applying the limit from upper minus lower, we got the value 729 and divide by 3. And after simplification, we got 243. So the exact integration value is 243 and iterative value is again 243. There is no concept of the decimal places value. That's the reason the calculation of error is 0.00 something. But if we got the exact value without the decimal places, the error value cannot be calculated further in this way. That's the reason we need the decimal places to calculate the error. And it is impossible that something has the value, something has the answer without the error. So another way I am calculating the value of error over here, I am placed that if we got the value, approximate value and exact value in the same aspect. So error from the exact value, that is the numerical iterative value, area under the curve, and approximate value, that is the conventional integration area under the curve by using the Simpson 3-8 rule, and convention value is respectively. After subtracting both the values in sign of mod, we got the error value, that is having 0. This is the absolute way of error that conventionally we are mostly calculate in class. The relative error we need to find by this way, that exact value minus approximate value divided by the exact value. So this is the way we can find the relative error value, that is also E of R 0. So multiply by 100, we also got the value in percentage, that is 0% error. So this is the way that how we can find the value of error in Simpson's three-edge rule. So up till now, we have discussed the third iteration value in numerical integration. In numerical integration, the third iteration value, the third iteration technique. Then number one that we discussed the trapezoidal rule. The second is the Simpson's one-third rule, and the third one that we discussed today is three-edge rule. So the three-edge rule is most important and a kind of value which also provide in less as minimum error in calculation. That's the reason if we in less number of iteration we got the less number of errors uh, in these kind of numerical integration technique in which area under the curve we calculate. So up till now, if anyone of you have any kind of question, query or difficulty, you may ask. I will answer the kind of question. And in comment chat box, you can also write your question. I will answer the kind of query if you have in your mind. So up till now, we having the participate Alimuddin, Hubeb, Shehbaz, and another one Shehbaz also. So these are the four participants we have, and there is no kind of question, query, or difficulty at your end. So uh, there is a query, but I have to answer by using the hands free. Hubab sir, you can you can I hearable? Can anyone answer? If you have any kind of question, someone has raised, please ask your question. I will answer.
Sir, you are audible, but your voice is very low. Can you please, just if you can raise your volume a little bit?
Okay. Now, can I? Am audible? Please ask your question. I will answer. Hopefully, my voice is clear at your end. I was discussed that we have discussed today the Simpson's three-edge rule, and in Simpson's three-edge rule, it's a powerful technique in which we got the least minimum as error, and in this way, we have the 8 intervals in which 9 iteration we need to calculate the numerical integration value area under the curve that at 0 to 9 lower and upper limit value having the function x square, and we need to calculate the error value at this end. So for the late person who joined right now, I am summarize the concept that the technique of numerical integration we already discussed today, that there are the three steps in which we calculate the value, and fourth one, the step we calculate the error. In first step, we uh, find the value of h, that is the numerical iterative difference from the first towards the last. That numerical iterative difference we got the value having 1. From 0 to 9, we place each individual value in the function from 0 towards the 9, and we got the second last column in this way. Further, in second step, we have the three-edge rule formula that yesterday we already discussed this formula in class, and implementation of this three-edge rule formula of Simpson's. In third step, we implement the formula and calculate all the values in fourth step. And in fifth step, we calculate the error value. And in fifth step, there are the three types of error, that is absolute, relative error, and in last percentage error. In all the value of percentage, that is relevant, absolute, and percentage error, all values of error are it having zero. So this is the technique of Simpson's three-edge rule in which we calculate the error value and all the kind of concepts. Hopefully clear at your end. If you have any kind of question, query, or difficulty at this end, you may ask. I will answer the kind of question and resolve your queries if you have in your mind. Khubaib Sab, if you have any kind of question, I think you raise your hand. I will answer the kind of question, resolve your queries. You may ask. Hopefully, all things have been clear and there is no kind of question, query, or difficulty at your end. Okay, in further, there are the four type of techniques of numerical integration, and we discussed the concept of numerical integration, that is Simpson's one-third rule, Simpson's three-eighth rule, and the first one technique. Can anybody tell me the what was the first technique of numerical integration that we discussed, and what was the name? That name was trapezoidal rule. So there are the four techniques of numerical integration, area under the curve, that we need to calculate and find the value in which technique provide us the least much as minimum error. So up till now we discussed today the third technique, that is Simpson three-edge rule in today's online session.